Okay, my friends, I'm a little bit excited. Physicists say they have taken a first look at electrons moving in real time in liquid water. Well, what did they say here? It says a research team led by Argonne National Laboratory physicists has isolated the energetic movement of an electron while freezing the motion of the much larger atom it orbits in a sample of liquid water. So they're saying that these electrons orbit the core, which is the nucleus, and they have photographed it somehow. I don't see any photograph of what I can show you, the actual photograph. Okay, my friends, before we get started, these are the particles that we found, and they are the exact same particles that Fermilab found, CERN, and all the rest of them, which is these little black and the white particles. That is literally a muon, and it is dark matter, and it is gravity. That is what causes light. These are the particles they found in these huge super colliders, and here's the particles we found in our experiments using only light. They started with huge masses of particles like this. We started with particles like this. So all we had is these little tiny particles, so we can see them right away. They have big things and they splash all over the place, and they see a big ball of debris like this. They take huge particles like this, and they take a batch of them, they smash them together, and when they hit just right, and that's very rare, they blow up into all the little bits and pieces go flying. Sometimes you have big chunks like this, sometimes you have little bitty ones like that. That's all, and sometimes you have them somewhere in between. So they have to look through all that until they found the same particles we found, which are these particles. After looking through all that debris, they found these two particles, which are the same two particles that we found in our light experiments. Those are the ones that Fermilab sees. And here it was right here. See the glowy little edge right around it? And they say they're black. They're always the same size. They're fixed. They're heavy. This has no weight whatsoever. I agree 100%. This is the black, and it's all glowy around it. Same thing. And these are the whites. Now, one electron literally is that right there. All right, just that. They call them gluons. It's actually an electron. They never knew the black part was attached to the white part. They always thought the white part was the electron. No, an electron is both of those together. And that's just like one of these, like a little tiny bar magnet. And you take two of these together and you have a photon. A photon bounces because it's completely surrounded by a magnetic field. The electron, only one of these, doesn't have a complete field. It only has a field on one side. So it wants to incorporate into something, and it won't bounce back. It'll incorporate as heat. And that's what electrons do. They don't bounce back. They want to attach to something. Just like you get static on you, that's extra electrons. They're floating around. They don't want to be by themselves. They'll just glue onto you until they can find a way to get to ground. So this is what we found in our experiments. And not only that, we were able to divide the black from the white, which is the holy grail in physics, which we did. And we put it through a venturi right here. This is Rod Warren discovered this just by accident. It stopped the black from going through and let only the white go through. That's called an electron shower, and the black is the muon. So we did exactly what they're trying to do, and not only that, we can direct it and shine it right down onto a receiving plate to collect free energy. So you've seen that I claim these are the only two particles that exist. And in my model right here, the dipole electron flood theory, there is nothing but these two particles, the black one and the white one. That's it. That's all that exists. And the more of them you put together, they will turn into a proton. All right, protons become stable for some reason, I can't tell you exactly why, approximately 1823 electrons, which is the black and white ones together, it seemed to become stable at about 1823. 1824 is a neutron, 1823 is a charged particle, but it's a proton, and it's fairly stable. Now, there's two possibilities here. One is that all of the white goes to the outside, and the black stays in the center. The other one is where you have layers of black, white, black, white, that type of thing. And the further they get out from the core, the less energetic they are. All right, so the red, the black is the dark matter, and that's this here right there. That's the muons. All right, the dark is the muon, the white is the electron. That's all. And how do I do that? Okay, now in here, the closer they are to the core, the tightly are they held. Blue is very, very energetic. Green is a little less, and red is not real energetic because it's so far away from the center. The closer it gets to the center, that's where you got your energy. And so this is really what it's made of. It's not made out of what they think a proton. They say a proton is one big ball like this. It's basically solid, but composed of what they call quarks, and they got a bunch of little names for it. But it's not. It's composed of all of these little particles like this. Now, when they smash these particles together, they get all those globs of things that I showed you before, which are all this kind of stuff. And then they dig through it until they find the little bitty ones. And that's what we started with, the little bitty ones, so we don't have to dig through anything. All right, listen to this now. It says the researchers initially came together to develop tools needed to understand the effect of prolonged exposure to ionizing radiation on the chemicals found in nuclear waste. Well, what is nuclear waste? Nuclear waste is broken up particles, and those broken up particles are this. This is nuclear waste. That's it right there. When you smash the big pieces together that are held very tightly together, these are tight, these are really strong held together, these atoms. You can do a lot of chemistry with them using enzymes, but when you bang these together, they're not going to break apart. The only way you can do it is hitting them so hard in these colliders that they just go crazy like that. But normally they're just going to bounce off of each other, swing away from each other because of their fields. There's a big field around here. You can't make these things hit head on. It's almost impossible. They send literally hundreds of billions of particles together, and they maybe get 25 or 50 of them to hit. I'm serious. That's how hard it is. We're getting every single one of ours to break it apart. And that's what they want to do, is break them apart. So that's what I mean by hit. We have every one of ours hit because we're forcing it to go through that venturi. So all of the light comes through and it hits there, and there's nothing can happen. So all the black ones, which are the muons, stay away. The white ones shower through there. This is basically what they really want to do. And the reason, what they're looking for is what happens as these things decay. All right, so here it is normal. That's a normal full-size atom. Everything's fine. Everybody's happy. No problem. Nobody's getting radiated. Well, all of a sudden, you create nuclear radiation, which is to break this into pieces. Now, this thing does not want to be like that. It's either going to suck some more into it, or it's going to spit some of those out. And when they spit out hard. And that's called nuclear radiation. Radioactivity. It's these things have to get out of where they are because they're not stable. That's instability. Now, we started with light, so we don't have really big stability problems. When you start with these, you got a lot of stability problems because you got all chunks. X means just a big blob coming off like that. These are sometimes look like this. Other ones, all kinds of different particles. But they normally either want to be like this, or they want to be like that. They're stable in this or that. They're not stable in this or that or this or that or that or this or this or this. They're not stable. A photon is what I showed you is like this. That's stable. These are stable. When you smash them into bits, that's when you get nuclear radioactivity. Now, the next thing that's absolutely critical to understand is light is this. I just showed you that's a stable particle. Those are stable. once you hit 1823 or 1824 of these particles together, they also become stable in that atomic nature, the proton. Now, these are not stable. They will never stay apart for more than a bazillionth of a second. You see how long they stayed apart? They want to get back together so bad that once they got through here, the black just jumped right on in. They want to be together. All right, here it comes. And that's acceleration. Light accelerates and slows down. There's so many problems with physics now. It's just unbelievable. This is the dark matter, the black, and it is the muons, and it also creates gravity. Because the white particles want desperately to attach to the black particles. And that's what happens in the atmosphere. As the light comes through, it goes right to ground. It hits right to ground. And everything that has white attached to it and is dark, because everything is dark and white together. There's nothing that isn't. There's nothing that isn't until we separate them. That's just not normal. It never happens, basically, that I know of, to have them separated like that. Now, so everything is together. The black ones here have the weight, all right? And the white ones want to attract to ground, so everything has gravity. The black falls to ground along with the white. All right? That's what it is. That's what gravity is all about. All right, apparently they don't understand the ultraviolet catastrophe. This is what happens, is you're supposed to emit an unbounded quantity of energy as the wavelength decreases, means it gets faster and faster. It's supposed to give off more and more energy, which it does. I'll show you that in a second. But then it didn't work. There was a problem. The term ultraviolet catastrophe was first used because all of a sudden there was no more energy. And here's what happens. This is the electromagnetic spectrum. All right, you start way down here with really, like sound, radio waves into the microwaves, which aren't any big deal. And then you get into infrared waves, which give you temperature, heat, but no real anything else. Then you get into the visible spectrum, where you can see the red, blue, and the green in the visible spectrum. But then as you get so high into the visible spectrum through the ultraviolet, and you hit the ultraviolet, now you have the ultraviolet catastrophe. And instead of the heat going more and more and more like it should go, it drops right down to 0 degrees. All right, it just goes down. There's no more energy left in the particle. All there is the black part of the particle, and that's what really does the disaster. All right, we're going to basically leave it at that, but here's some other ones that I'm looking at here now. Physicists create 5 new isotopes. Isotopes are just the same molecule with less or more extra dipoles. So that's no big deal. Now, this is interesting. Physicists determine gluonic gravitational form factors of a proton, which that's true. They're gluons inside of the proton. That's all they are, is a ton of different gluons. Now, here's the one that really intrigues me. Physicists determine distribution of the strong force inside the proton. I have to look at this because I showed you what I'm seeing. For us, the strong force is going to be either in the center, pulling all the stuff to it, or all of those stuff attracted to it. Let me put it that way. They don't really pull anything, I don't think. The white seeks the black. Now, it could be this, or it could be in layers like this. They appear to be showing them in layers. I'm going to have to look into this. But look, they could create one-dimensional noble gas. They get all this stuff. Capture direct images of noble gas and massive neutron stars. New research says light on structure of carbon nucleus. Well, carbon nucleus is just one of something like this. With I forget how many I said, but there's, I think it was like 25,000, something like that, particles like this. This is what's in the nucleus. All right, listen to this. This is where I think we can get free energy. They're saying protons are built of 3 quarks, which is not correct, that are bound together by the strong force. The strong force is what I'm interested in. At its peak, this is more than a 4-ton force. The strong force, 4 tons it takes to rip that apart. So you'd have to use 4 tons would have to apply to a quark to pull it out of the proton. They're not quarks. They're dipole electrons. But that's where all your energy comes from, is these, to separate the two. We can separate them for nothing. We didn't use any force whatsoever. We put them through a Venturi. All right, so don't forget, this is Jefferson Labs, and they're talking about, these are all the different little dipoles that are inside of a proton. That's all. Now, I don't think they really understand it, but it's similar to what I'm talking about. The only thing is that the core is where real tight stuff is, and then the electrons surround it. But it takes 4 tons force to pull one of those electrons out of there. That's why electricity is just so staggeringly strong. It says the measurement reveals insight into the environment experienced by the protons' building blocks, which are dipoles. They're starting to get there. All right, this is all just coming out within the last few days. Physicists determined gluonic gravitational form factors of the proton. The gluons are the particles I showed you before, the black and white together. It says little is known about the inner mass density of the proton, which is dominated by the energy carried by these gluons. That's all there is gluons in there. There's nothing but gluons. All right, and they're either like this together in their discrete packages, or else they have separated and done this. And I know that blacks can separate from the white, so that's no problem whatsoever. But these are the only 2 particles that exist. The 2 of them together are a gluon. There is right there. These are the gluons. And you take 1823 in a ball like this, and you have a proton. You take 1824, it's a neutron. And then mass, more and more and more mass, they turn into bigger and bigger elements. But in between every one of these elements, there's thousands and thousands of gluons that they never accounted for. And those account for all the different isotopes and half-lives and all of the debris that comes out when they smash these to bits. And these just so desperately want to get back to stabilization that they are dangerous. That's where you get radiation. All right? Nuclear radiation is, they either want to give up a batch of stuff to get stable, or they want to pull in a batch of stuff to get stable. But whatever they do, if they're touching you when they do that, well, then the stuff they're pulling out or pushing in is going to cause a problem to you. So that's it for today. I think I'm showing that dipole electron flood theory is basically, at this point, it's undeniable. I've shown that we've done all the work. It's done. It's exactly the same as they say at Fermilab. There's no difference whatsoever. These are the same 2 particles, 100% for sure. And we separated them, which means that we did that 4-ton force. Remember I told you, in order to pull the black and the white apart, it requires 4 tons of force. So when we get this white, we should be able to use that to drive your car, do anything you want. We've separated it for free. And that is exactly what's done in a generator. When you run a generator and you turn it online, your motor's going, and you turn it on, because it's got to and throw those electrons off. And it takes tons and tons of energy to do that. And that's why electricity is so powerful, and it weighs nothing. If you take your car, and it's a 4,000-pound car, and you are totally empty, no electricity left in it whatsoever, it weighs 4,000 pounds. You fill it right up to the top of electricity, and it weighs 4,000 pounds. You drive it around all day, you come back, it's empty again, it still weighs 4,000 pounds. The white part weighs nothing whatsoever. All right, I'm going to more or less leave it at this. This is what they're talking about, is to come in real low energy and create these high energy electron showers, which are the white particles that I showed you. All right, the black particles stay away. That's here, the muons. You see that? And you could put these things here in a box like that, carry it around, have more energy to ever be able to use. As far as I'm concerned, I think so. These are the electron showers, high energy electron showers, high energy, tons of force required to rip them apart. Not for us. We put them through the Venturi. The muons have to stay back, and the electrons go out and turn into electricity. That's exactly what we did. We took the laser, shot it through here. The black can't get through. It's just too big. It pops back, and the white gets squirted, literally squirted through there, down into whatever battery, running car, whatever you want. And you could put a ton of these in a little thing like that and have all these little outlets, anything you wanted. Carry it around. You don't need a grid. There's no contamination. You're only working with light, so you're never going to get injured. Don't put your eyeball down in the middle of it, but that's all right. Other than that, you're good. By the time they get this far apart, they're back together again. They're just nothing more than light. All right, so I love you all. If we could do something like this. I can't believe they won't talk to me about this, and they refuse to discuss. From all the places that we thought, like Fermilab, they refused to talk to me. And that's their particles, and that's the ones we found. I guess there's just not enough money in it from what we did, I guess, because it didn't cost us hardly anything to do this.